a frigate and propelled with full power. She was armed on the main deck, and her model was so designed as to enable her to fight her bow and stern guns in line with the keel, in which important qualification she stood almost alone in the Navy. 96 Illustrated London News, May 12, 1849. The value of private shipbuilding yards able to undertake admiralty work at short notice was abundantly proved during the Crimean War. In 1854, at the commencement of the Crimean War, said the Times in an article on the building of warships in private establishments, when Admiral Napier found himself powerless in the Baltic for want of gunboats, it became imperative to have 120 of them, with 60 horsepower engines on board, ready for next spring, and at first the means for turning out so large an amount of work in so short a time puzzled the Admiralty. But Mr. Penn pointed out, and himself put into practice, an easy solution of the mechanical difficulty. By calling to his assistance the best workshops in the country, in duplicating parts, and by a full use of the admirable resources of his own establishments at Greenwich and Deptford, he was able to fit up with the requisite engine power 97 gunboats. This performance is a memorable illustration of what the private workshops of this free country can accomplish when war with its unexpected requirements comes upon us. Altogether during the Crimean War 121 vessels were fitted with engines for our government by Mr. Penn. 2 paddle-wheel gunboats, Nix and Salamander, were launched in 1851 by Messrs. Robinson and Russell for the Prussian government, which exchanged them during the Crimean War for a frigate called the Thetis, and they were renamed Recruit and Weezer. They were double-ended and could steam in either direction without turning. The paddle frigate Danzig, built by the same firm for the same foreign government, had the peculiarity of being able to carry guns on her sponsons. The last wooden battleship built for the Navy was the Victoria, 121 guns, launched in 1859, commissioned in 1864, and discarded in 1867. She was engined by Maudslay with horizontal return connecting rod engines indicating 4,400 horsepower and giving her a speed of 12 knots. The Ban and Brune were built by Scott Russell as improvements on the Salamander, and were on the longitudinal system with wave lines, and they had internal bulkheads separating the engine and boiler rooms from the bunkers. The success of the floating batteries at the Crimea was held by the French to justify the construction of a sea-going ironclad, and the Gaulois resulted. Experiments in America had shown the possibility of the plan, but the French naval architect, Dupuy de Lomé, considered that it would be sufficient to plate existing vessels. The Gaulois was a big wooden ship cut down and iron-plated. This stirred the Admiralty to activity and the Warrior was ordered. The launch of this vessel on the Thames was regarded as an event of national importance, and in spite of the cold day at the end of December 1860 on which she took the water, the attendance was exceedingly large, even the tops of the tall chimneys of the neighborhood having been let out for the day to enthusiastic sightseers. She was frozen down to the ways so firmly that it was with the utmost difficulty that she could be got into the water at all. Tugs, hydraulic presses, the hammering by hundreds of men on the ways, and the firing of cannon from her deck to start her by concussion were all tried separately and then together, and at last the ship glided slowly into the water. The beauty of her lines was remarkable as she floated in her light trim, and afterwards, when she was properly equipped and in sea-going trim, she was one of the most beautiful ships the country ever possessed. She was iron-built throughout, frame and plating being alike of the metal. She was 420 feet over all, 58 feet in breadth, and 41 feet 6 inches in depth from spar deck to keel. She was of 6,177 tons builder's measurement. Her engines, which were of 1,250 nominal horsepower, weighed about 950 tons, but her bunkers only held 950 tons, or enough coal for 6 days steaming. She was divided into 27 watertight compartments at the bows and stern, and as the whole of her sides were so armored as to afford protection to the vital parts of the ship, it was stated that even if the fore and stern parts of the ship were shot away, the center would remain as a floating battery. The Waterwitch. The Waterwitch is chiefly remarkable for the trial given in her to Mr. Ruthven's system of hydraulic propulsion. A small boat was fitted with the machinery and tried on the Thames. A vessel provided with the Ruthven apparatus was built to the order of the Prussian government in 1853, and for many years worked satisfactorily on the Oder. The chief engineer of Portsmouth Dockyard, when testifying to the government as to the capabilities of the Ruthven method, said it afforded extraordinary facilities for maneuvering under steam, and he saw no reason why a speed should not be attained with it equal to that of the paddle or screw. A vessel called the Searing was built by the Belgian shipbuilding firm of Cockerill and fitted with a Ruthven propeller, and when tried against a paddle wheel vessel of the same form, tonnage and horsepower was found to have about 10% or greater speed than the other. The testimony of the chief engineer of the Portsmouth Dockyard resulted in the Waterwitch experiment. The hull of this vessel was constructed by the Thames Iron Works and Shipbuilding Company, and the design of the engines and the construction of the enormous turbine wheel, of which the propeller consists, were entrusted by the Admiralty to Messrs. Dudgeon. The Waterwitch was built of iron and was of 778 tons measurement, 162 feet in length by 32 feet in breadth, and 13 feet 9 inches in depth. She was flat-bottomed, broad in proportion to her length, and double-ended and had a rudder at each end. Her armor consisted of a belt of plating 4·12 inches in thickness at the water line and centrally on her broadside, with armor-plated bulkheads across her upper deck, the object of the latter arrangement being to enable her to fight her guns over her deck in line with her keel, through gun ports in the thwartship bulkheads as well as through broadside ports. For the machinery, and in the bottom of the vessel near the center, was a long and shallow iron box with its length in the direction of the vessel. The lower side of this box had an immense number of small rectangular orifices, admitting water from outside and under the ship's bottom, the passage of the water being controlled by valves which were only opened when the engines were at work. The turbine wheel drew the water in through the bottom of the vessel and ejected it through copper propulsion pipes and nozzles, through an aperture on each side of the ship, a little below the water line. The propelling power of the hydraulic wheel is obtained from the force and volume of the column of water ejected by the wheel from the discharge pipes, on a principle that a gun recoils on being discharged, but with this difference, that the recoil from the water wheel is continuous. If the column of water were discharged towards the stern, the vessel moved forward, and if towards the stem it moved in the other direction. If discharged in both directions, the vessel remained stationary, and if discharged forward on one side and towards the stern on the other, the vessel turned either on her center as on a pivot, or if the pressure were greater in one direction than in the other, in a circle the size of which depended on the pressure of the discharge from either set of nozzles. No reversing of the engines or of the hydraulic wheel was required under any circumstances, the direction and force of the discharge being regulated by a series of valves. The hydraulic wheel was fixed immediately over the sluice valves and water box, and revolved in a cast iron circular case 19 feet in diameter. The wheel was itself 14 feet 6 inches in diameter and weighed 8 tons, and was fitted with 11 vertical or radial arms and blades. The engines were of 160 nominal horsepower, and steam was supplied by 2 ordinary tubular boilers. At her trial the Waterwitch covered the measured mile in long reach in 6 minutes 20 seconds. At other trials later in the day she averaged 9 knots. The shape of the vessel and the fact that she could be steered in either direction with equal facility were of undoubted advantage from the point of view of maneuvering, but the trials can hardly be called successful so much as experimental, as it was ascertained that she would probably have done better had her nozzles been differently placed and provision made for altering the size of the nozzles according to the speed at which the vessel was required to travel. The machinery itself, however, worked beautifully. The government ordered a number of comparative tests to be made in which the efficacy of the water-witch method could be judged against that of the double-screw system installed in the gunboats Viper and Vixen, all three vessels being of the same size. The two gunboats were not the best of their kind as they had double sternposts with a cavernous recess between them and flat overhanging sterns. Mr. M. W. Ruthven, son of the inventor of the system, it being under his father's patent that the water-witch machine was built, in addressing the Institute of Marine Engineers a few years ago, said, "My efforts to make a ship safe, from an engineer's point of view, lie in the method of propulsion. My plans are to apply all the engine power of the ship to pumps for propulsion, and which can be used for pumping out leakage and propelling at the same time. In the largest pump I have made, 800 indicated horsepower discharged 350 tons of water a minute, and propelled the vessel faster than her sister ships with twin screws. The hydraulic propeller is of greatest value for the highest speeds, and has the greatest power of control. As the hydraulic is capable of subdivision to a great degree, the greatest amount of safety is possible. After an experience of 60 years of hydraulic propulsion, I am still of opinion that it is the means by which greater safety can be obtained at sea, and by which the highest speeds can be obtained with safety and economy." 9797 Institute of Marine Engineers Transactions, Volume 9. This, however, was said before such phenomenal speeds were obtained with turbines and combined turbine and reciprocating engines. A number of lifeboats fitted with jet-propelling machinery have been built by, among others, Messrs. Thornycroft, and have given every satisfaction. Whatever be the advantages of the system, and they are many, the drawbacks are very great, and the hydraulic method has been generally condemned because of the friction engendered by the pumping of such large quantities of water, and the probability of the inlet orifices becoming choked by sand, mud, or floating matter. Notwithstanding its evident advantages, the screw propeller, whether single or double, had many enemies. It was asserted to be the cause of premature decay in both wood and iron vessels, and stringent orders were even given to ship captains to use canvas except in extreme cases when steam was absolutely necessary. "Our screw navy is, therefore," said a paper of that period, "more of a sailing than a steam navy." The twin screw arranged by Messrs. Dudgeon was claimed to have developed the principle in such a way as to leave no doubt of its superiority over the single propeller. Twin screws were no new thing at this time. Captain Smith, known as Target Smith because of his movable target in use on the Excellent, had experimented with some with a considerable measure of success, but it was Messrs. Dudgeon who solved the problem of twin-screw propellers for ocean-going steamers. They demonstrated that as good results could be got from two small propellers as from one large one. The first application of twin screws on the modern principle was made by Messrs. J. and W. Dudgeon in the Flora in November 1862. Twin screws were tried by the Admiralty some years earlier in the construction of the iron-cased floating batteries, but were driven in those vessels by one motion from the engines. The adoption of the twin screw in their case enabled the Admiralty to build vessels that required only a moderately light draft of water, and carried, for their tonnage, an enormous weight of armament and armor, besides the weight of their engines, but the vessels had no increased powers of turning nor could they maneuver rapidly under steam in any circumscribed space. The double independent screws overcame these drawbacks. A small vessel in the Clyde worked two screws also, with two rudders, the idea, as acknowledged by the adapter, having been derived from the model exhibited in the exhibition of 1851 by Mr. John Sturdy, Master Shipwright's assistant at Portsmouth Dockyard. An unusual degree of interest attached to the trial of the steamship Flora by reason of the fact that each of her twin screws was to be operated by its own engine. In the light of future events, it is worthy of note that up to this time it was thought that the twin screw would be useful for smaller vessels and gunboats carrying 6 guns or less, whereas the Flora, as representative of ships capable of carrying large armaments of guns, with considerable engine power, and a light draft of water, and with a power of maneuvering such as could not be possessed by a single screw vessel, marked a step forward in the march of improvement which was destined to have far-reaching results, both in the Navy and the mercantile marine. So important was the trial deemed that the Admiralty sent special representatives to report thereon. The Flora was an iron vessel, 150 feet long, 22 superscript 12 feet beam, and 13 feet depth, and of 365 tons. She had 2 independent engines and screws, the latter being placed one under each quarter, and therefore in front of the rudder, in contrast to the prevailing system of placing a single screw right astern and behind the rudder. The cylinders of the 2 engines were 26 inches in diameter, with a stroke of 21 inches, and the propellers were each of 7 feet diameter with a pitch of 14 superscript 12 feet. She had 2 tubular boilers working at 30 pounds pressure, and 1 high-pressure boiler working at 50 pounds pressure, the latter boiler being intended to be used for producing a steam blast in the chimney and to dry the steam from the 2 common boilers. The engines were of 120 horsepower collectively. She was rigged as a fore and aft schooner. The principal test to which the vessel was subjected tried her capabilities of being maneuvered. With the helm hard over and the engines going full speed ahead, the first circle was made in 3 minutes 14 seconds, the next in 1 second less time, and the third circle in 3 minutes 16 seconds, the diameter of the circle being about 3 lengths of the ship, but slightly diminished each time. The ship was then tested with 1 screw working ahead and the other astern. 1 circle was made in 3 minutes 39 seconds, and another in 3 minutes 49 seconds. In making these circles, the action of the ship's hull was extraordinary, the central part being stationary, and both ends moving round equally. The circle was made on a pivot from the ship's midship section. The vessel was then put in a straight course, stopped, and from a state of rest the engines were started, one ahead and the other astern, the circle being completed in 3 minutes 55 seconds and the diameter being as before within the ship's length. 98 The Flora proved herself faster than any other steamer of her size and horsepower, and became, thanks to her speed, one of the most successful blockade runners during the American Civil War. 98 Illustrated London News, November 29, 1862. HMS Minotaur. The experiments in the Flora, and afterwards in the Hebe and Kate, which were of about the same dimensions and power, were considered so satisfactory that a trial on a larger and more important scale was made in the summer of 1863 with the Aurora. This was an iron vessel, 165 feet in length, with a beam of 23 feet, and a depth of 13 feet 6 inches. Her engines, of 120 collective nominal horsepower, drove 2 3-blade screws, each independently of the other. The screws were 7 feet in diameter and had a pitch of 14 feet 6 inches. The cylinders were of 26 inches in diameter with a stroke of 21 inches. On her trials she steered equally well with either propellers or rudder, and in the matter of speed passed everything she came across, including the Sea Swallow, one of the fastest paddle boats on the Thames. The distance from Tilbury to the Nowher, 20 nautical miles, was done in 1 hour 17 minutes, an almost unparalleled rate of speed, considering the vessel's horsepower of engine and hull displacement. 99 times, August 1863. The experiment was the first twin-screw boat built for the Navy. The engines were direct-acting, horizontal, high-pressure, and drove two 3-blade propellers, having a diameter of 3 feet 6 inches. She was built by Dudgeon in February 1863. Some interesting experiments were also carried out in February 1863 with a steamer called the Edith, built by Dudgeon with a view to testing further, for the benefit of the Admiralty, whose representatives were present, the advantages of the twin screw for naval maneuvering purposes. This vessel was not constructed for the Navy, however, but for commercial service across the Atlantic. She was rather larger than the Experiment, being 175 feet in length, 25 feet in breadth, and drawing 9 feet aft and 6 feet 6 inches forward. The twin screws, each driven by its own engine, were 3-bladed and had a diameter of 8 feet 6 inches, and a pitch of 16 feet. On her trial run down the river with the Admiralty officials on board, a speed was attained of nearly 12 knots against the tide, and nearly 15 knots with the tide, the engines averaging 100 revolutions a minute under 28 pounds steam pressure. The vessel turned a complete circle in 3 minutes 29 seconds with her own center as a pivot, and then the action of both screws was suddenly reversed. Their action upon the vessel was instantaneous, the revolving motion of the ship being changed to the opposite direction with the greatest ease. The maneuver was repeated several times, and the vessel thus represented a revolving battery mounted with heavy ordnance, too heavy for training upon any given object by ordinary appliances. The hull became the carriage for such heavy guns, and trained them upon any given point by revolving under the action of the screws alone. Photo. G. West and Son. The König Wilhelm, German Navy. Photo. G. West and Son. The Baden, German Navy. The American Navy up to the time of the Civil War was not taken into very serious consideration by the other nations, but in that momentous struggle the Federals awoke to the need of thoroughly effective vessels and built them quickly. They were the last to take to iron ships of war, but they more than made up for the delay. In scarcely a year after the launch of Ericsson's Monitor, the first ship of its class possessed by the federal government, there were built, or building, close upon 20 of these vessels. Various modifications were introduced, but the principle was the same. This was the turret on the deck, where the armament of the vessel was placed, it being sought to construct an effective battery for defensive operations rather than to build a sea-going ship. The contest between the Confederate iron-protected Merrimac and the Federal wooden warships, which ended disastrously for the latter, and the battle between the Monitor and the Merrimac proved that the old wooden three-deckers had become obsolete and that they would be perfectly useless against a steam ram like the Merrimac and harmless against an ironclad ram like the Monitor. For a time rams and turrets were regarded as all-important. The extreme in this combination was reached in the French ironclad ram Taureau. She was one of the most peculiar warships ever constructed. Seen end on, she looked like a tremendous buoy, surmounted by a turret, a funnel, and two masts. A side view showed that an immense bow extended forward as a long ram, and that the turret was situated near the bows. The prow was of bronze and weighed 11 tons, and projected some 40 feet under the water. Her deck view represented her as almost pear-shaped, with cylindrical sides, and she had her greatest beam at about the water line. She was ironclad for about 3 feet above the water line amidships and aft, but the turret and bows had 5-inch armor. Altogether she was about 197 feet long by 48 feet beam, and carried one heavy gun in the turret. A combination of three-decker and ironclad ram was the French warship Magenta, constructed in 1862. She had an enormous ram like the Taureau and carried 80 guns, and was barkentine rigged. In England, Captain Coles began in 1859 to urge the construction of vessels of the cupola or turret type, and after the lesson of the famous contests in America between the two ironclads, the British Admiralty decided to try Captain Cole's boats experimentally. He advocated the cutting down of the three-deckers into one-deck ships, carrying on this one deck one or more turrets or cupolas in which the guns should be placed. These turrets were capable of being turned so that the guns in them could be fired in any direction, and he proposed that a portion of the bulwarks should be hinged in order that they could be let down when it was required to fire the guns, and thus form a sort of additional protection to that portion of the ship's side above the water line, while when raised they would add to the seaworthiness of the vessels by keeping the water off their decks. Vessels built according to Captain Cole's plans, it was contended, would be floating defenses which would be at once thoroughly manageable, impervious to shot, movable with ease, and seaworthy. Nor would they be so monstrous and unsightly to a nautical eye as the inventions of our American cousins. They would be fitted with masts and yards, having the one peculiarity of being made of one uniform size, so that ships of all classes abroad could be furnished at depots, in case of accident, or ships meeting each other could exchange with or supply their comrades, to quote from one of the descriptions published at the time. Another advantage was that the conversion of heavy frigates and line-of-battle ships into iron-plated vessels, fitted with the Cole's shield, could be effected at a comparatively moderate cost. Experiments with the cupola were tried on the Trusty and Hazard with success. The standardization of masts and rigging was another point on which Captain Coles laid stress. The cupola system had so much to recommend it that Sir William Armstrong wrote to the Times endorsing it as solving the problem of working the heaviest guns. Could shipbuilding have stood still at that period, the system would have been an unqualified success, but the rivalry between armor makers and gun makers was so intense that no sooner did an armor plate maker produce a plate impenetrable to existing guns and projectiles than the gun makers set to work to produce a gun and projectile which should smash the armor plate. Photo: G. West and Son. HMS Devastation. Photo: G. West and Son. HMS Thunderer. The steam corvette Pallas, launched at Woolwich in 1865, differed materially from any other vessel hitherto constructed. She was originally intended to be built of iron, but as the necessary machinery was not then in existence at Woolwich, she was constructed of wood and iron-plated, and had a belt of armor to protect the most important parts. She was rigged as a ship so that she might keep at sea for a considerable time, the sails enabling her to economize her fuel. In order to increase her seaworthiness, she was made high above the water, her fixed bulwarks being 18 feet above the water level. She was also designed to be able to fight end-on. The engines were of 600 horsepower, and, to counteract the enormous strains the screw propeller was expected to impose, a new system of stern construction was adopted whereby the stern posts and deadwood were connected with the sides by internal iron bulkheads, decks, and flats, and external brass castings. The Pallas was 2,372 tons burden, and was intended to be a faster vessel than any wooden frigate in the Navy. The fastest wooden frigate afloat and complete then was the Mersey, which once got up to 13 knots an hour. The Pallas was provided with Mr. Reed's new bow, known as the U-bow from its shape. This bow gave considerable buoyancy where it was needed to support the ram, but its shape created a wave forward and thus militate against the vessel's speed. HMS Minotaur, launched in 1865, was almost the last of the great sailing warships carrying a ram and having powerful auxiliary machinery. She had 5 square-rigged masts, and all 5 topsails were on the divided principle. The German ironclad Prinz Hendrik, built by Laird Brothers of Birkenhead, and launched in October 1866, was bark-rigged, and was fitted with Captain Cole's tripod masts. She was also fitted with revolving turrets, hinged bulwarks, and a sliding funnel. The Hercules, begun in June 1866, and launched in February 1869, was one of the best specimens of the entirely iron-built, iron-armored frigates the Navy possessed at that time. Her ram bow did not protrude so far as in former vessels and only weighed about 5 tons. The armor plating on the sides of the ship weighed 1,145 tons. The total weight of metal worked into the ship was 4,252 tons. The bulwarks were of wood, but below them the first 2 strakes were of plate 6 inches thick. Next was a strake of 8-inch armor covering the lower portion of the main deck or central box battery, then 2 strakes of 6-inch armor, then a belt of 9-inch armor along the water line, then a strake of 6-inch plates resting above the double skin of the hull itself. The 9-inch plates were backed by 10 inches of teak, inside of which was an iron skin 1 superscript 1/2 in thick, supported by vertical frames 10 inches deep and 2 feet apart, while further stiffening structures were also included. The engines worked up to over 7,000 indicated horsepower. The vessel also afforded an illustration of the tendency to reduce the number of guns and increase their weight. To add to her steering capacities, she had a balanced rudder which was itself jointed and hinged upon the line of pivot. HMS Dreadnought. The carrying of such quantities of armor was against the maintenance of high speed at sea, and accordingly the unarmored iron frigate Inconstant was launched later in the same year. She carried 16 guns and was faster than any other warship afloat. The Prussian ironclad König Wilhelm, built by the Thames Iron Works and Shipbuilding Company, from designs by Mr. E. J. Reed, in 1869, was commenced for the Turkish government, and was built on the longitudinal system, having a series of wrought iron girders or frames extending from end to end of the ship. There was an inner skin on the inner sides of the frames and ribs, as though one ship was inside another. She was then the heaviest vessel ever docked in the Thames, as she weighed 8,500 tons. Her armor was 8 inches thick amidships and tapered slightly towards the ends. The year 1869 was remarkable for the introduction into the British Navy of large ironclads without masts or sails and relying upon steam alone for their propulsion, and these vessels also demonstrated the most perfect form then understood of the turret ship as applied to a sea-going warship of large capacity. The Devastation, built at Portsmouth, and the Thunderer at Pembroke, were the first of this class, and were claimed to be more formidable than any other warships in existence both for offense and defense. They were each of 285 feet in length and 4,406 tons, as compared with the first ironclad Warrior, 380 feet and 6,019 tons, and the Minotaur, of 400 feet length and 6,021 tons. The Warrior's armor was 4 superscript 1/2 inches of hammered plate that would break under the impact of heavy shot, that of the Minotaur was 5 superscript 1/2 inches of rolled armor, in each vessel there being a strong backing of teak and iron plating built into the frame. The 2 turret ships had 12 inches of rolled armor plating on a teak backing built into an immensely strong framing 18 inches thick, and the whole was backed up with an inner skin of iron plating 1 superscript 1/2 inches thick. The thickest armor then in use in the French Navy was 8 superscript 1/4 inches and was carried only by rams of the Bellier class. These vessels also included an improvement in the bracket frame system of construction, first introduced in the Bellerophon by Mr. Reed. The brazed torque monitor of the Devastation type was regarded as an improvement on the American types of monitors. The turrets were mounted on Captain Cole's system and each turret carried 2 30-ton guns. The ships were driven by independent twin screws and had a speed of 12 superscript 12 knots. In 1870 the ill-fated Captain was lost. She was designed by Captain Coles and built by Messrs. Laird as a sea-going turret vessel. The principal armament was 4 25-ton Armstrong guns carried in 2 turrets, one fore and one aft. These turrets were 27 feet diameter outside and 2 superscript 12 feet inside, half the thickness of the wall consisting of iron plating. This ship behaved admirably on her trials and also on an experimental cruise, and was sent to sea with the fleet in September of that year. From some reason never explained satisfactorily, she capsized without warning, and went down in a few seconds during a gale in the Bay of Biscay before daylight on the morning of September 7. Only 19 of the 500 persons on board were saved, among the drowned being Captain Coles himself. This disaster evoked such an amount of criticism as to the vessel's stability and seaworthiness that no more of the type were constructed, the turret ships subsequently built being modifications of the principal. Photo. G. West and Son. HMS Lightning. Photo. G. West and Son. HMS Tartar, torpedo boat. Armor-plated batteries found their chief representatives in the batteries of the time of the Crimean War, of which the Glatton and Terror may be regarded as types, and the double-turret principle was developed in such vessels as the Cerberus. The Terror was built by Palmers for the destruction of the Kronstadt forts. She had 3 masts carrying square sails on the foremast, and excessively sloping sides and bluff ends, and would form a remarkable contrast to the graceful lines of the modern battleship. The Terror was built, armor-plated, and launched in about 3 months, thanks to Sir Charles Palmer's invention of rolling instead of forging the armor plates. The Battle of Tsushima afforded naval architects some valuable lessons, and the Dreadnought and the Lord Nelson may be regarded as the first results. The Japanese-built Satsuma is virtually on the same lines, there being little to choose between the Satsuma and the Lord Nelson. The Dreadnought's turbine machinery drives 4 shafts, and immediately aft of the inner shafts are twin rudders to give the ship greater steering facilities. The Admiralty adopted turbines, according to an official statement, because of the saving in weight and reduction in number of working parts, and reduced liability to breakdown, its smooth working, ease of manipulation, saving of coal consumption at high powers, and hence boiler room space and saving of engine room complement, and also because of the increased protection which is provided for with this system, due to the engines being lower in the ship, advantages which more than counterbalance the disadvantages. There was no difficulty in arriving at a decision to adopt turbine propulsion from the point of view of seagoing speed only. The point that chiefly occupied the committee was the question of providing sufficient stopping and turning power for purposes of easy and quick maneuvering. Trials were carried out between the sister vessels Eden and Wavani, and the Amethyst and Sapphire, one of each class fitted with reciprocating and the other with turbine engines. The necessary stopping and astern power will be provided by astern turbines on each of the 4 shafts. These astern turbines will be arranged in series, 1 high and 1 low pressure astern turbine on each side of the ship, and in this way the steam will be more economically used when going astern, and a proportionally greater astern power obtained than in the Eden and Amethyst. Messrs. John I Thornycroft & Co.'s first torpedo boat for the British Navy was the Lightning, of 18 knots, but the firm's Tartar, launched in 1907, broke all records by traveling at 35-67 knots. The latest destroyers have a speed of 33 knots, though the coastal destroyers have a speed of only 26 knots. Another remarkable feature in the Navy of late years has been the number of vessels to be fitted with oil-burning apparatus instead of coal. The destroyer Mohawk, built by J. Samuel White at Cowes, is 270 feet in length, 25 feet beam, and 765 tons displacement, and contains water tube boilers and turbines of 14,000 horsepower, and attained a speed of 40 miles an hour. She carries no coal, oil fuel being used, of which her bunkers can take 73 tons. The Tartar's record was broken by the destroyer Swift, 345 feet in length with a displacement of 1,800 tons, and having quadruple turbine engines giving her a speed of 36 knots. The cruiser Invincible, launched by Armstrongs at Elswick in April 1907, is a first-class armored cruiser 530 feet in length and of 17,250 tons displacement, and has turbine engines of an equivalent horsepower of 40,000 and a speed of 25 knots. Photo. G. West and Son. HMS Lord Nelson. Photo. G. West and Son. HMS Invincible, armored cruiser. The construction of warships has resolved itself into a struggle to attain an ever-increasing speed combined with offensive power and great range of action, and warships of varying types have been produced with startling rapidity, so that one powerful vessel after another has been evolved, each superseding its predecessor in some degree, until there are dreadnoughts and super-dreadnoughts carrying guns and armor and possessing a speed undreamed of a few years ago. Among smaller vessels, torpedo boats, destroyers, scouts, cruisers of various classes, commerce destroyers, cruiser battleships, and submarines now take their places in the nation's fleet. There is no telling in what direction the next development will be. The Battle of the Boilers has played an important part in the development of the warship, and it is safe to say that had this struggle not taken place to produce a boiler which should give a great pressure of steam quickly, the speed of the warship as now known would not have been attainable. Twin screws are succeeded by triple screws, and these are to be followed by quadruple screws. The second-class protected cruiser Bristol, launched at Messrs. John Brown & Co.'s Clydebank establishment in February last, is of special interest as she embodies the introduction of yet another method of propulsion. When it became known that an experiment was to be made, there was some speculation as to whether the gas system was to be tried, as the experiments in the gunboat Rattler are understood to have been successful, and it is well known that more than one engineering firm has been giving attention to the subject. The Rattler experiments did not prove that the requisite power could be developed by the method, and the Bristol experiment is an installation of the Brown-Curtis turbine, this vessel being the first of recent years for the British Navy in which Parsons turbines have not been placed. She is of 4,850 tons displacement and is to have a speed of 25 knots. 4 sister ships, also building, are fitted with Parsons turbines. The Bristol will have 12 Yarrow water tube boilers, and the furnaces will use either coal or oil. 2 other British warships, one an improved Bristol, are to be fitted with Curtis turbines, besides vessels for other powers, and another experiment which will be watched with considerable interest is the combination of Parsons and Curtis turbines proposed to be placed in the 32-knot destroyers under construction for the Argentine government by Camel, Laird, and Co. Foreign governments, the French especially, have made many experiments in warship building and designing, for the attempts to develop fixed types have failed in this country as elsewhere, as the type has been generally superseded almost before the specimen vessel has been completed. This was particularly the case with the turrets when first introduced. The barbette system has descended from it, and in turn has been subjected to numerous changes. The amount of sail carried by modern gunboats and cruisers, if any, is reduced to the smallest quantity, the masts being little else than signaling poles, while in the big battleships and cruisers the masts, which were at one time of the military pattern and were used as hoists for ammunition, being made hollow and of large diameter for the purpose, have in their turn given way to skeleton masts and tripods, and combinations of the two, of a strictly utilitarian character. The bringing down of a mast, fitted for wireless telegraphy, at the first round in some firing practice recently, showed that naval architects have not yet reached the last word in the development, or diminution, of the masts. Some exceedingly powerful battleships have been built in this country for foreign nations, among the latest being the Minas Gerais, by Armstrongs on the Tyne, for Brazil, which represents all that is most modern in the construction of a warship, this vessel and her sister being two of the most powerful battleships ever designed. They show, too, what private yards can accomplish. The Minas Gerais, Brazilian Navy. Many of the vessels which defeated the Russians at the Battle of Tsushima were built in this country. Both Germany and Japan, which were among Britain's best customers for warships, now depend, entirely in the case of Germany and almost entirely in that of Japan, upon their own shipbuilding yards. The Germans have been building warships of the Dreadnought class and making such improvements as they thought suited to their needs, and of late years have been producing a number of vessels equal in power and speed to the British ships, and, if some people are right, of even greater fighting capacity in every way. The rise of Germany to the position of a first-rate naval power has been rapid, and the sacrifices the country has made to obtain its magnificent navy have been great. The American Navy has developed in its own way. The naval architects of the United States have been unfettered by the traditions of the navies of other countries, and their products have been remarkable for the number of vessels designed to meet special circumstances. This was particularly the case during the Civil War, when all sorts of steamers, from excursion boats to tugs, were pressed into service, and many gave an exceedingly good account of themselves. A remarkable vessel which was expected to revolutionize naval warfare was the destroyer, in which a special make of dynamite gun was fixed, but it was hopelessly outranged by other guns. The opposition to steam in the Navy was as bitter in America as in this country when the innovation was first proposed. James Kirk Paulding, a member of Van Buren's cabinet in 1837, disliked steamers so much that he wrote that he would never consent to see our grand old ships supplanted by these new and ugly sea monsters, and elsewhere he wrote, "I am steamed to death." In 1858 the American naval architect, John Willis Griffiths, built to the order of the American government the gunboat Pawnee, which was fitted with twin screws and a drop bilge to increase the stability at the least expenditure of engine power. The Pawnee carried a frigate's battery, but it is stated to have drawn only 10 feet of water. He also, in 1866, designed and constructed triple screws for great speed. The United States decided upon a very powerful navy a few years ago, and sent a splendid fleet on a tour round the world as an object lesson. As it is contended that the life of a battleship as a fighting unit of the first class is only 15 years, an extensive modernizing process has been going on. The sister ships Kentucky and Kearsarge were constructed with superimposed turrets, 2 fore and 2 aft, the lower turrets having 2 13-inch guns and the upper turrets 2 8-inch guns each, but this method of placing the turrets has not commended itself to naval architects of other countries, and has not been repeated in the American Navy. The warships Wilmington, Kearsarge, Missouri, Arkansas, West Virginia, Charleston, Virginia, North Carolina, and Delaware are among those built by the Newport News Shipbuilding and Dry Dock Company, and several have been constructed by Messrs. Cramp at Philadelphia and by the Union Iron Works at San Francisco. The battleship of the future, in the opinion of one eminent shipbuilder at least, will be very different from existing types. Messrs. Vickers, Sons, and Maxim, who are no mean authorities on warship construction, were stated recently to have been engaged in elaborating plans for a mastless vessel, propelled by a system of gas machinery, without funnels or other deck obstructions, of a greater speed than any warship afloat, and able to fire 10 12-inch guns on either broadside and 6 of them either right ahead or astern, without counting a number of smaller guns. Such a vessel would be propelled by 4 screws. Photo. G. West and Son. The Kearsarge, U.S. Navy. Photo. G. West and Son. The San Francisco, U.S. Navy. Chapter 12 Miscellaneous application of steam power tugs, cargo boats, floating docks, ferries, icebreakers, yachts. Eccentricities of design. Conclusion. Not the least important of the types of steamers which throng the ports of the world, or which used to do so, for their number is decreasing, is the tugboat. Up to a few years ago it played a most important part in the work of a port. Every sailing ship entering port usually engaged the services of a tug. Many ports, like that of London, could not be entered at all by a large sailing ship without the services of a fair wind ahead, as sailors often call the tug, and in the waters outside the port of London the tugboats found one of the best pitches in their business. To be towed safely into port might mean a saving of many days in avoiding the waiting for a wind. The tug was equally useful to a ship leaving port, as she might not only tow her into the open sea, but might even take her right out of sight of land altogether, in helping her along until a favorable slant of wind was met. At ports like Liverpool sailing ship masters often, when wind and tide were favorable, brought their ships into port under full sail without a tug, though probably 3 or 4 of them kept her company in the hope that their services would be required, as they generally were when the time came to enter dock. Nowadays sailing ships are few in number and are becoming fewer, and steamers seldom require aid. They enter and leave port under their own steam and even at times dispense with a tug when passing through the dock entrance, their own steam or a steam capstan ashore being found sufficient. But a certain amount of towing has still to be done, and the tug is then able to prove herself indispensable. She has often to tow a ship from one coast port to another, while for rescue work on the coast their services mean all the difference between success and failure. A lifeboat is towed to a wreck or vessel in danger. The tug, which has perhaps been several hours fighting her way forward against a howling gale and a terrific sea which threatens to overwhelm her, then stands by, and a paragraph in the papers to that effect is about all the recognition she gets. Yet the perils undergone by the men on the tug are no less real than those of the lifeboatmen. Year in and year out the tugs pursue their calling, and it must indeed be bad weather that will induce a tugboat captain to seek the shelter of a harbor if his bunkers are fairly full and he sees a chance of doing business. The feats performed by some tugs are extraordinary. They will undertake a voyage of a few thousand miles as serenely as one of as many yards. Cleopatra's Needle, in its strange cylinder ship, was towed to this country, after being lost adrift in the Bay of Biscay, by a well-known London tug. Among the most remarkable recent feats are the towing of immense unwieldy floating docks from this country to South American West Coast ports. It is not too much to say that a tug owner will cheerfully undertake to tow anything that will float from any one seaport to any other. The cargo steamer until 10 or 15 years ago possessed no special features. It was simply a big box carrying propelling machinery and as much cargo as possible on the smallest attainable registered tonnage. Such vessels were usually loaded and discharged by the necessary machinery on the quayside, while if the transfer of cargo had to be to or from barges alongside, the operation was likely to be tediously performed by means of a derrick or two, or a gaff with tackle that might or might not be worked by a steam winch. The increasing size of vessels and the use of steel for steamer building rendered imperative the adoption of faster methods, and the demands for special steamers adapted for particular trades brought about the development in cargo steamers of special types. These types have to a very large extent taken the trade away from the steamer of the tramp class, which wandered from port to port taking cargoes of anything or everything from anywhere to anywhere. They were usually slow and uncomfortable boats, and the complaints made as to the condition of some of them were fully justified. The demand for better cargo accommodation was met by the supply of vessels of various types which are a tremendous advance upon the old tramp, and their advent compelled the builders of ordinary cargo carriers to produce a better and larger steamer in every way, and fitted with modern appliances for the rapid and satisfactory handling of cargo. The cargo tramps, built about 1902, were on an average about 350 feet long, 2,800 tons gross and 4,000 tons dead weight. In build they were of the poop, bridge, and forecastle deck type with main deck below the upper deck, and fitted with double bottoms. The appliances for working cargo are extraordinarily complete and effective. To each hatch there are usually 2 winches and 2 derricks, having 5 tons lift each, with, as a rule, a heavy derrick capable of lifting from 20 to 30 tons, the last is portable, so that it can be used at either of the 2 main hatches. Cathead davits have been dispensed with as, with stockless anchors, they are not required owing to the anchors stowing up the hawse pipes. Officers, &c., are berthed in deck houses built on the bridge deck, leaving the bridge tween deck clear for cargo. Electric light and steam heating are fitted to all rooms, advantages not enjoyed by older boats. About the year 1904 the shelter deck type reached its present stage of perfection, the advantage of this type being increased cargo capacity on a small net tonnage. The accommodation of officers and engineers is fitted in midship deck houses and side houses. Much more attention is now paid to the ventilation of the holds and 'tween decks, more especially in coal carriers, where efficient ventilation is of the highest importance. The adoption, within very recent years, of wide-spaced pillars in holds and 'tween decks has greatly improved the facilities for stowage of large cargo. The 4 desiderata of a modern cargo boat are that she should have a low registered tonnage in comparison with her capacity, ample water ballast tanks, large hatchways, and holds as free from obstruction as possible. 3 or 4 methods are practiced by builders for attaining these objects, and every builder has made modifications of them as time has shown the necessity of the changes to meet varying trade conditions. The principal types of cargo vessels are the turret, trunk, cantilever, and side tank. The earlier modern ocean-going steamers were usually flush-decked. This left the machinery openings bare in the deck, so a bridge was added for their protection, and the flush deck was further encroached upon by the addition of a forecastle and poop. In some cases the quarter deck was raised, which was an awkward arrangement on account of the change it necessitated in the structure and framing, and in others the bridge and poop were joined. What is sometimes called the 3-island type, a very appropriate name in rough weather when the steamer takes a sea on board, came into great favor. It consists of a forecastle, bridge, and poop, and many vessels of considerable size have been built in that style. The cattle trade was responsible for some important changes in design, the wells where the cattle are carried being given iron and steel shelters, which thus form the shelter decks, a type of light deck introduced into the superstructure of most ocean-going steamers. The secret of the turret steamer is strength without unnecessary weight. Every ton of steel that can be kept out of a ship without reducing her strength adds a ton to her carrying capacity. This object is partly achieved in the turret steamer by the large amount of flanging adopted in the construction of these vessels. This is shown in the whole of the sheer strake and stringer plates, in the deck and frames of the cellular bottom work, and with great success in the joggled plating of the hull. Since 1895, when the Doxfords introduced a new method of rolling ships' plates with joggled edges, they have built all their vessels under this system, making packing unnecessary. The turret gives longitudinal strength in the hull and leaves the hold clear. The strength is so great that in a steamer in which, by the substitution of deep for ordinary frames, all internal supports, beams, and girders are dispensed with, a clear hold is obtained. The firm claims that 58 cubic feet per ton dead weight under hatches is secured against 52 to 54 cubic feet per ton in the ordinary type. Thus the turret carries more on a given displacement, and having a lower registered tonnage, can earn more freight and save expenses. There are several designs of turret steamers adapted to different trades. Their suitability for bulk cargo, such as coal, or for large and heavy packages, is evident, while other types are equally suitable as passenger steamers, not a few lines having adopted them. Another advantage is that deck cargoes of wood can be carried with perfect safety on the turrets. Some of the cargo boats designed for the ore and coal trade have their machinery right aft, and their holds are absolutely clear of obstruction of any kind whatever. Many of these are mastless but are fitted with twin derricks, a 10,000 ton boat carrying as many as 7 pairs. The first of the mastless type was the Teucer. Convention fixed the depth of hold at about 15 feet, but now a depth of 26 feet and more is becoming fairly common. All cargo vessels are built on the box girder system, which ensures great strength and capacity, and permits of enormous hatchways, and marine engineers have solved the problem of providing greater speed without additional expense. Messrs. Docks Ford, in their latest attempt to solve the problem of the easily shifting cargo in bulk, proposed that vessels intended for this trade should have inner upright walls fitted some distance from the hull, and so arranged that when the vessel is heeled over within the usual range of inclinations of a vessel at sea, the weight of the cargo and the buoyancy create a restoring couple in all conditions of loading. The spaces between the cargo hold and the outer shell may be left empty or used for water ballast as required. In some instances the bottom is reduced in depth as much as the loading regulations will allow. Among the more notable features of recent years in cargo boats specially adapted for the coal, iron ore, and other deadweight trades is the patent cantilever frame type of steamer built by Sir Railton Dixon & Co., Limited, Cleveland Dockyard, Middlesbrough, on the Haraway and Dixon patents. This type of boat has the advantage of having totally unobstructed holds with very large hatchways and an additional 75% water ballast, which is placed in the tanks inside the cantilever construction at the top of the holds under the deck. In these steamers the space on either side and under the decks is used for water ballast, which is carried in triangular tanks at either side of the vessel, immediately beneath the main deck. The tanks extend from the coamings to the sides of the ship, the greatest side of the triangle being towards the cargo and supported by the cantilever framing. The tank framing and plating increase the strength of the hull materially. The sloping topsides thus formed prevent bulk cargo shifting. An advantage to the owner is that the tanks are exempt from tonnage measurement. When these tanks are filled with water and also the lower and peak tanks, the vessel is seaworthy even if the cargo space is empty. This additional water ballast has the special merit of immersing the ship deeper when in ballast only, consequently giving more power to the propeller and rendering the ship more manageable when light, as well as supplying unique security in case of damage, for when one of these boats is loaded and the topside tanks are empty, they correspond to the air tanks of a lifeboat and thus prevent the ship from sinking. These vessels in some cases have been fitted with shelter decks right fore and aft for the carriage of cattle and horses, and indeed would be suitable for passenger service, for which the very easy rolling movement would be a great recommendation. This type of vessel has been on the market for about 4 years and already some 200,000 tons have been built. One of the largest steamers built on this plan is the Echinga, 405 feet long, 56 feet beam, and 28 feet 8 inches molded depth. She was built in 1908 for the Adelaide Steamship Company. Her net register is 2,245 tons, her deadweight capacity 8,400 tons, and her measurement 11,000 tons. Her topside tanks contain 1,350 tons, and her total water ballast is 3,200 tons. In the steamers built by Messrs. William Gray & Co., Limited, of West Hartlepool, water ballast is carried not only in the double bottoms but inside tanks, the inner skin of the double bottoms being carried a considerable distance up the sides. A hull within a hull is thus formed, the intervening space being used as water ballast tanks. Not the least advantage is the great additional strength the ship is given. The trunk system of shipbuilding adopted by Messrs. Ronner & Sons, Limited, of Stockton-on-Tees, differs from the turret by having a double wall on each side, and has not the rounded turret base. The steamer Thor, built for a Norwegian owner, has only one hold, no less than 250 feet in length, the engines being placed aft. Messrs. R. Craggs and Sons, Limited, of Middlesbrough, have made a speciality of building tankers, and were the designers and contractors for the first ocean steamer to load oil in bulk. Their stringerless system of construction is, they claim, the last word in transverse framing, and has numerous advantages for single-deck vessels. During the last 3 years 3 distinct innovations in steamship construction have been made. All 3 are of a revolutionary character, and 2 are likely to have no small influence upon the construction of both passenger and cargo steamers, while the third is of great importance for the rapid loading and discharging of coal and ore cargoes. The first of these is the Isherwood system of longitudinal ship construction, in which the transverse frame as ordinarily understood is dispensed with, but deep transverse web frames are placed at intervals of 15 to 18 feet apart and extending right round the ship, forming both frame and beam together. These frames are intersected by longitudinal frames consisting of sections of convenient form, preferably bulb angles, spaced about 20 to 30 inches apart, just as transverse frames are under the ordinary system. The fore and aft frames are fitted beneath the deck also, and are spaced from 30 to 50 inches apart. In the double bottom the fore and aft girders are formed of plates and angles. The first general cargo vessel on this plan was the Craster Hall, launched in February 1908 by Messrs. William Hamilton & Co., Limited, Port Glasgow. Her length is 392 feet 6 inches, breadth, 50 feet, depth, 29 feet to the upper deck, dead weight, 7,300 tons. The Monitoria, the Iroquois and the Navajo. 2 oil tankers, the Paul Pakes and Gascony, have been built by Messrs. Craggs and Sons on this system. One of them grounded off Calais with a cargo of oil or benzene on board, and on being dry docked for examination was found to have no damage to her plates whatever. All the steamers built on the Isherwood plan have a marked absence of vibration even when running light. The corrugated steamship Monitoria, launched in the summer of 1909 by Messrs. Osborne Graham & Co., Sunderland, to the order of the Ericsson Shipping Company of Newcastle-on-Tyne, is another departure from accepted ideas. She is an ordinary tramp steamer so far as dimensions and engine power go. Her only difference, and it is an important one, is that she has 2 corrugations running along each side between bilge and load water line, and extending from the turn of the bow to the turn of the quarter. These corrugations do not project very greatly, but according to the inventor, they so affect the stream and wave action around and under the vessel that a source of wasted energy is prevented, and more power becomes available for propulsion. The Monitoria's dimensions are, length, 288 feet 6 inches overall, breadth, 39 feet 10 superscript 12 inches, the breadth over the corrugations is nearly 42 feet. The space for bulk cargoes is greater than on her sister ships by the cubic contents of the corrugations, but the tonnages remain unaltered. As a sea-going ship it was found that the corrugations made her much steadier, acting as though they were bilge keels, and that the coal consumption was less, notwithstanding that she made faster time than her sister vessels under precisely similar conditions. The Monitoria, transverse section. The third innovation is the application of the belt conveyor principle to a collier. The steamer Pallion, in which the machinery is installed, is equipped throughout with twin belt conveyors which, traveling fore and aft the vessel in a space under the cargo, carry the cargo towards the stern, whence it is carried on other belts at the front of the poop for delivery. The latter belts are carried on swivel booms which can be raised or lowered or moved sideways, so that the cargo is delivered direct by the belts into railway trucks on the quay or into barges, and the operation can be conducted at the rate of 250 tons an hour on each side of the vessel simultaneously. Under this system no chutes are used, and there is no handling of the coal. The pallion requires only about 6 hours to discharge a full cargo with 6 men, as against over 100 men and 11 hours in the ordinary way. Her water ballast tanks can be emptied or filled as fast as the cargo is placed in her or taken out. She was built by the Doxford firm at Sunderland for a Newcastle shipping company. The carrying of petroleum in bulk has spread enormously of late years in both steamers and sailing vessels specially designed for the purpose. In all such vessels the method of the subdivision of the holds into tanks is of the greatest importance, together with that of ventilation, and every builder and owner of such vessels has his own theories as to the best means to be adopted. A later type of tanker has the engines astern. A further innovation in this class of steamer is to fit them for burning oil fuel, the two big tankers Oberon and Trinculo having had the necessary installation placed in them last year at Smith's Dock, North Shields, sometimes called the home of tank steamer repairing work. An economical method of transporting oil in bulk across the Atlantic is adopted in the case of the steamer Iroquois, which herself carries about 10,000 tons of oil in bulk, and also tows with her the sailing barge Navajo, carrying an equal quantity, one set of engines thus doing duty for both cargoes. The Navajo is the largest sailing ship in the world, is schooner rigged on all her 6 masts, and is able to make her way to port in case she becomes separated from her consort. The floating dock is one of the most interesting of the many developments in connection with the naval and mercantile marine of the second half of the 19th century. Like all innovations, floating docks were received with derision. Now they have proved their worth, but circumstances are easily conceivable in which all the marvels they have already accomplished will be far eclipsed by what they may be called upon to do. In the case of a naval battle, for instance, it may be a matter of impossibility for a crippled warship to enter a dry dock, or even to get to one, but a floating dock can be sent to meet the injured warrior and possibly save it from going to the bottom altogether. The floating dock is a sort of raft, and the first man who ever hauled a boat from the water upon another boat or raft to repair it started the idea of the floating dock. The first real floating dock, as the term is now understood, was probably that which was improvised in the Baltic Sea, so tradition says, by the skipper of a vessel which had sustained some damage in those waters. He bought an old hulk, removed the stern, and in its place constructed a flap gate. His vessel was then floated into the hulk, the flap gate was closed and the water pumped out. Floating docks of this type were almost the only kind known up to the beginning of the 19th century, and are in use today at some ports for small yachts, fishing boats, and vessels of similar dimensions. With the growing size of vessels, greater docking facilities became necessary, and, as the commerce of the world increased and ports were developed, demands arose for docking accommodation which could not always be met, owing in some cases to financial difficulties, and in others to the engineering difficulties connected with the localities. As a solution of the problem, the floating dock, as it is known today, was invented. In spite of the opposition with which it was greeted, the new contrivance held its own, and its merits became generally recognized. The difficulties and the cost of constructing dry docks are very great, and the time taken in the work may run into years. One dock, indeed, is stated to have taken 15 years to complete. As an instance of rapidity of floating dock construction, the Vulcan Company of Stettin required a dock 510 feet long and of 11,000 tons lifting power at short notice. The complete dock with all machinery and fittings was launched within 7.5 months, and within 8 months and 13 days of the inception of the project, the dock, after being towed across the North Sea and moored in place at its site, was sunk ready to receive its first ship. The Havana dock was delivered at Havana within 11 months after the signing of the contract for its construction. The actual time expended on it, dating from the day the first plate was laid until the complete dock was launched, was 6 months and a day. Both these docks are of over 10,000 tons lifting power. How long would it have taken to excavate and build graving docks capable of receiving vessels of the size that these docks can accommodate? No dry dock can take a vessel larger than itself, and in reckoning the dimensions of a dock for receiving purposes it must be remembered that its dill is a fixture, that the width of the entrance at the dill must not be made greater than the strength of the structure will permit, and that though a dock may in other respects be able to receive a vessel it cannot do so if that vessel through any mishap should draw as much water as that at depth of dill, or if in heeling over, its bilges should be wider than the width of the dock entrance. None of these drawbacks apply to the floating dock. These immense modern structures of steel and iron can receive vessels longer than themselves, and in the case of the offshore docks, can receive vessels wider than themselves. Should a vessel be heavily down by the head or stern, a floating dock can be tilted to lift it, and should the vessel be heeling over, the dock itself can be inclined so that it shall receive it without difficulty. Yet another advantage is that the floating dock can be used in any kind of ordinary weather. Lying at its moorings it is head on to wind and sea. The amount of surface it opposes to the direct action of wind and sea is comparatively slight. The very massiveness of its structure reduces longitudinal and lateral motion to a minimum, especially when submerged. Even with a fairly heavy sea running, a damaged and leaking vessel can be brought upon the dock where its weight, added to that of the dock itself, makes the combined structure additionally stiff, so that the necessary repairs can be undertaken in safety as soon as the vessel is lifted, and with as much ease as if the dock and its burden were in still water. Floating docks also can be used at any state of the tide, but he would be a rash man who attempted to warp a vessel into an ordinary dry dock with the tide running past the entrance with any degree of strength. Old floating dock at Rotherhithe, circa 1800. The earliest type of the modern floating dock is that known as the box dock. It consists of a pontoon divided into cells or compartments, and having on either side a large wall also divided into compartments arranged in tiers, the ends of the structure between the walls being open. The earliest of these docks were made of wood, and compared with those of later date were of small dimensions. One of the most noteworthy wooden docks was that at Rangoon, launched in February 1866, and having a length of 300 feet, with a breadth of 90 feet, and an inside breadth of 70 feet, and able to take vessels drawing from 15 to 16 feet of water. There is also at Altona a wooden floating dock built in 1868 and still in active use. It is 138 feet in length, and can lift vessels up to 420 tons register. The early floating docks were usually in transverse section like the capital letter U, and followed fairly closely the form of the round-bottomed ships of the time. As the girder principle, however, became introduced in shipbuilding, it was recognized that floating docks must be constructed approximating to that shape, and modern floating docks are now built rectangular in transverse section, though in constructional details this form is a modification of the U shape. Floating docks themselves are in occasional need of repair, and when it was found that they could be constructed of a greater size than any then existing dry dock, it being customary to dry dock them for repair, the necessity arose of devising a means whereby the repairs could be made without taking the floating dock out of the water. Sometimes a dock can be tilted endways or sideways as occasion requires, for a portion of its underwater surface to be exposed, but there is obviously a limit to this operation and to the effectiveness with which work under these conditions can be carried out. This difficulty was met by constructing docks on the sectional principle, whereby any two sections of a floating dock constructed in three sections can lift the other one, while with offshore docks, which are usually built in two sections, either can lift the other. An attempt to careen the old U-shaped Bermuda dock nearly capsized her altogether. One of the earliest, if indeed not the earliest, of self-docking double-sided docks is that associated with the name of Mr. Rennie, and now generally known as the Rennie type, or, in an attempt made at uniform classification of self-docking docks by Messrs. Clark and Stanfield, who probably have had greater experience of floating dock designing than any other firm in the world, the sectional pontoon dock. This is an extremely simple form of dock, consisting of a series of similar pontoons connected together into a hole by the walls or side girders, which run along each side on top of the pontoon, to which they are attached by bolts. In self-docking, any particular pontoon can be unbolted from underneath the walls, allowed to sink slightly, and then be drawn out sideways, turned half round, and lifted on the rest of the dock. The type is also very suitable for erection abroad, for the pontoons can be built and launched separately, and, being but light structures, require no expensive launching slips, whilst the side walls can be erected on top of the pontoons after they are afloat. 100 Modern Floating Docks, by Lionel Edwin Clark, MINA. The first Bermuda dock, launched at North Woolwich by Messrs. Campbell, Johnstone, and Co., in September 1868, was the largest built up to that time, and was ordered by the Admiralty for the use of British ships in the West Indian Squadron. It was 381 feet in length, 123 feet 9 inches in extreme breadth, and had a total depth of 74 feet 5 inches. Caissons enclosed a dock space of 333 feet by 83 feet 9 inches in width, capable of receiving a vessel of 3,000 tons. The section of the dock is of U-form throughout, though for convenience of towing, a tapered bow of wood was added, and remained until it rotted off at Bermuda. The dock was designed by Mr. Campbell. The sides consisted of a cellular space 20 feet in width, and midway between the inner and outer skin was a watertight bulkhead, running the whole length of the structure. Each side was subdivided by longitudinal bulkheads into 3 compartments, named from the bottom, the air, balance and load chambers, and was further subdivided into 24 watertight cells. The dock was fitted with 4 steam engines and pumps on each side. Hitherto all floating docks had been built in sections, shipped to their destinations and erected there. The Bermuda dock, however, was towed there, experimentally, and so successfully was the work accomplished that the towing of floating docks across the ocean has become the rule, and some wonderful feats of towing have been performed. This dock, becoming unequal to the requirements of modern shipping, gave place to the present dock built at Wallsend in 1902. Model of the Bermuda dock. The length of the present Bermuda dock is 545 feet over the keel blocks, its width of entrance 100 feet, and it is capable of normally taking vessels drawing 33 feet of water over keel blocks 4 feet high. The walls themselves are 53 feet 3 inches high, and 435 feet in length, and they form girders of enormous strength. 3 pontoons, secured to the lower portions of the walls by fishplate joints, lugs, and taper pins, form the bottom or deck of the dock. The middle pontoon is a rectangle 96 feet by 300 feet, the end pontoons, each 120 feet long, taper for 49 feet towards their outer extremities to facilitate towing. At this immersion the walls have a freeboard of 3 feet 6 inches, which in urgent cases might be safely reduced by a foot or more in order to increase the depth of water over the blocks. Its lifting power up to pontoon deck level is 15,500 tons, but by utilizing the pound formed by the bulwark surrounding the pontoon decks, additional lifting power up to 17,500 tons can be gained. The dock, without its machinery, weighs 6,500 tons. When called upon to perform its maximum lift, the dock is sunk until the summit of its walls is but 2 feet 6 inches above sea level. Water is admitted into the 3 pontoons and the 2 side walls, and from them removed by 8 16-inch centrifugal pumps at a rate sufficient to lift an ironclad of 15,000 tons in 3.5 hours. In order that the dock may not tilt as it rises, the whole is divided into 56 divisions, each of which is separately connected with the pumps. By turning off cocks, water can be left in any desired divisions, and the dock forced to incline in any direction for purposes of cleaning and repairs. When undergoing its official tests, the Bermuda dock lifted HMS Sans Perel over 11,000 tons, and after its arrival at Bermuda it received and raised completely out of the water HMS Dominion, when that vessel was badly damaged through stranding and was so down in the water as to displace nearly 17,000 tons. It is specially important that a structure of this kind should be self-docking, that is, able to lift any part of itself clear of the water. To expose the bottom of one side, the dock is first lowered to a depth of 20 to 21 feet, the water inside the wall compartments being brought to the same level as that of the water outside. The dock is then raised by emptying the pontoons, and when these are exhausted the water is released from the side to be exposed until the outer corner is 2 feet or more clear. The pontoons are lifted in turn by withdrawing the pins of one, and allowing it to float, while the rest of the dock sinks. The pontoon is then made fast to the walls at its floating level, and the dock emptied, so exposing the whole of the bottom of the raised pontoon. The 2 end sections can be treated simultaneously, and floated if required onto the central portion, but the latter must be moved only when the other pontoons are in position. Electric lights and hauling machinery are distributed over the dock. A crane capable of lifting 5 tons runs along each wall from end to end. A somewhat similar dock to that at Bermuda, slightly shorter but of greater lifting power, was designed for the Navy Department of the United States of America, and constructed by the Maryland Steel Company at Baltimore, and stationed at Algiers near New Orleans. Its length is 525 feet over blocks, its entrance 100 feet, and its lifting power up to pontoon deck level no less than 18,000 tons, making it as regards lifting power then the most powerful dock in the world. This lifting could be increased to 20,000 tons by using the pound. Its hull weight is 5,850 tons. Self-docking of the Bermuda dock, well-heeled. Bermuda dock, center pontoon self-docked. It is interesting to note the different methods adopted by the governments of the 2 countries for the shoring or berthing of the ships on the dock. The English custom in the case of ironclads of the pre-dreadnought era, and also that of Italy and Japan, is to support the armor belt on more or less vertical shores inserted under an angle iron firmly attached to the belt. These shores are put into position as the ship is rising, and, as the water recedes, more and more shores are inserted. The Bermuda dock has large and heavy altars constructed for this purpose. The American custom is to strengthen the bilges of their ironclads with strong bilge docking keels, forming, with the keel proper, a level bottom. No shores are required beyond those necessary to center the vessel, and no great care is required in adjusting the berth, and one set of bilge blocks does for all sizes of vessels. The American plan affords a great saving in weight and quantity of shores, and, what is more important, a great saving in time, not only in the preparation of the berth and centering of the ship, but also in the actual lifting. With the American plan it would be perfectly feasible to dock a vessel completely in the time required to center and adjust her with shores disposed according to English practice. The Penarth floating dock was constructed in 1909 at Wallsend to the order of the Penarth Shipbuilding and Ship Repairing Company, Ltd. The dock is of the offshore or single-walled type, and is one of the finest of its kind. It has an overall length of about 380 feet, an extreme width of 75 feet, and is capable of accommodating vessels having a beam of 55 feet, with a draft of water up to 18 feet, and a displacement of 4,200 tons. Its pumping machinery consists of 4 centrifugal pumps and engines, for which steam is supplied by 2 large Babcock and Wilcox boilers, working at 160 pounds pressure. This plant can lift a vessel of 7,000 tons dead weight in 3/4 of an hour. For self-docking, the dock is divided transversely into 2 equal portions, each with its own pumping plant, so that either section can be docked by the other portion. A powerful steam capstan is fitted at each end of the top wall to assist in warping vessels into position when lifting or otherwise. It has 8 mechanical side shores in addition to the usual accessories for facilitating the rapid handling of vessels, such as bilge shores, roller fenders, rubbing timbers, and bollards. A duplex reciprocating pump, with a capacity of about 100 tons per hour, has a connection to the main drain of the dock, and enables practically the whole of the water to be pumped out of the dock. On the delivery side, the pump is connected to a service pipe, which has connections at intervals for 3-inch delivery hose. The pump is capable of throwing 3 jets of water to a height of 40 feet. To enable this floating dock to enter the wet dock in which it was to work, the entrance to which is several feet less than the width of the dock, a joint was provided running the whole length of the pontoon. On arrival of the dock in Penarth Roads, this joint was disconnected, and the separate sections towed into the wet dock and reconnected, and the necessary attachment made to the quay wall. Bolted sectional dock lifting a vessel. The Callao floating dock, the towing of which to its destination from the Tyne was the most hazardous towing feat ever accomplished, merits special attention, both on account of the completeness of its equipment and of the extraordinary interest which was manifested in its journey. It is one of the double-sided self-docking type, known as bolted sectional, and is divided into 3 separate portions. It is capable of lifting vessels having a displacement of 7,000 tons, but it is so designed that this lifting capacity may be increased to 9,500 tons at some future period by the addition of a 4th section, making the overall length about 510 feet, the present length being 385 feet. Its extreme width, i.e., the clearance between the rubbing fenders, is 70 feet, and the draft over keel blocks is sufficient to take vessels drawing 22 feet. As in previous floating docks built on the Clark and Stanfield principle, each section has its own independent pumping machinery and steam supply. Such usual accessories as keel and bilge blocks, mechanical side shores, rubbing timbers, flying gangways, head capstans, and are supplied, and there is a heavy mooring outfit